So we're continuing with examples of direct proof, and here's going to be another one. It says, show that if x cubed minus 7x squared plus x minus 7 equals 0, then x equals 7. So again, the strategy with direct proof, we're proving an if-then statement, which means we should start by assuming the hypothesis, which is what has been done here. You do some work with it, and then you talk about why you can conclude the conclusion of the if-then statement from your work. So you go through this, they're doing some algebra, they're doing some factoring, and the way they say it is, since all of this, if it's equal to 0, we either need x squared plus 1 to be equal to 0 or x minus 7 to be equal to 0. And then the argument continues, since x squared plus 1 can never be 0, and we must have that x minus 7 equals 0, thus x equals 7. And I know what you might be thinking, it's saying never be 0. We know that if we have the complex numbers, then x squared plus 1 could be 0. So we just assume that we're living in the real numbers. Okay, if you'd like to pause and give this one a try, this hands-on exercise here, a try, it's very similar, go ahead and do that. And again, notice the way they wrote things. They didn't just show math and then they're done. They used words. So pay attention to the way they used the words. Okay. Let's look at another example. So it says the last example demonstrates a technique called proof by cases. Okay, why are they saying that? It's because once we have kind of a fork in the road, we have either x squared plus 1 equals 0 or x minus 7 equals 0. We have to technically examine each case separately and argue from there why we can conclude what we need to conclude. So it says case 1 would be x squared plus 1 equals 0. Case 2 would be x minus 7 equals 0. And we looked at the two cases separately, and that's how we were able to get to our conclusion. Let's look at a more specific case of proof by cases. So it says, show that if an integer n is not divisible by 3, then n squared minus 1 must be a multiple of 3. Okay. So they already mentioned a letter in the thing we're trying to prove, so we can just use that letter n and make sure it plays the role that the n does in the statement. But a lot of times, if they didn't say the n, it says, if it were to say, show that if an integer is not divisible by 3, then the square of that integer minus 1 must be a multiple of 3. That would be a way to say that in words without mentioning n. And in that case, you would want to start with let n be whatever you need it to be. In this case, an integer that's not divisible by 3. Either way, it's a good idea to start your proof by saying something like that. So they start with let n be an integer that is not divisible by 3. When it is divided by 3, the remainder is 1 or 2. So think about that for a second. When I divide any number by 3, the remainder has to be 1 or 2, or it could be 0. It can't be anything more than 2. So if you want to see a quick example, let's do 54 divided by 3. Well, 3 goes into 5 once, and And then 3 goes into 24 8 times, and the remainder is 0. What if I do 55 divided by 3? It's going to be, well, 3 goes into 5 once. 5 minus 3 is 2. 3 goes into 25 8 times. And now the remainder is 1. And if we try 56 divided by 3, 3 goes into 5 once. 5 minus 3 is 2. 3 goes into 26 8 times. 26 minus 24 is going to be 2, which means we have a remainder of 2. Now we do 57 divided by 3. I say 3 goes into 5 once. 5 minus 3 is 2. 3 doesn't go into 27 8 times like the other ones. It goes in 9 times. But what if I said 8? If I said it goes in 8 times, I would be doing 27 minus 24, which is 3. It's kind of weird to say remainder 3, so I don't want to do that. And also I didn't think of a number that was big enough that where, is the number of times that 3 goes into 27. So I have to think about that again. 3 goes into 27 9 times. 9 times 3 is 27. The remainder is 0. So we can only get a remainder of 0, 1, or 2 when we're dividing by 3. And we can generalize that. We're actually going to talk about that pretty soon. So let's go back to what the proof is saying. Again, it said when it is divided by 3, in other words, we're talking about n. So when n is divided by 3, the remainder is 1 or 2. Hence, n is of the form 3q plus 1 or 3q plus 2 for some integer q. That gives us 2 possibilities to explore, which is why this is an example of proof by cases. So I have case 1. If n is 3q plus 1 for some integer q, then what does n squared minus 1 look like? Well, you do the algebra, you work it out. When you subtract 1, you're left with 9q squared plus 6q, and you can factor a 3 out of that, and the remaining part is an integer. And remember, that's what it means to be a multiple of 3. It means I can write n squared minus 1, I can write n squared minus 1 as 3 times some other integer. Okay. Again, how do we know that 3q squared plus 2q is an integer? Well, q is an integer. When I square q, I get an integer. Multiply it by 3, still an integer. If I take q, multiply it by 2, that's an integer. So now I have integer plus integer, which is integer. All right, case 2 is very similar, except you're assuming n is 3q plus 2. So you work it out. You end up with, again, 3 terms that all have a common factor of 3. And you factor that out, and you state that 3q plus squared plus 4q plus 1 has to be an integer. Again, by a similar argument as what I said for 3q squared plus 2q. In both cases, we have shown that n squared minus 1 is a multiple of 3. Okay, so a couple of hands-on exercises for you to try. Pause the video, give them a try.